Hello, and welcome to Quiet Learning for Sleep. This is your peaceful space to unwind, to let go of the day, and to drift into deep, restful sleep while learning softly about our universe. Here, we take gentle journeys through calm ideas, stories from science and nature, space and time, history and life, all whispered at a soft pace, without rush, without noise, and without pressure. You do not need to focus or remember anything. This is learning the quiet way, where your mind floats and drifts and rests, while curiosity stays softly awake in the background. If you'd like, before you get comfortable, you can subscribe and gently like this video. Doing it now means you won't forget later, and it helps others like you find this calm, sleepy corner of the world. Now, allow your breath to slow just a little. Let your shoulders relax. Let your thoughts soften, like clouds drifting across a calm evening sky. There is nowhere you need to go, nothing you need to do, and nothing expected from you here. This time belongs to rest, comfort, and gentle curiosity. And if you drift to sleep along the way, that is not only allowed, it is welcome. So settle in, let yourself melt into stillness, and allow your mind to float quietly as we begin. In the early 1970s, humanity stood at a quiet crossroads in its exploration of space. The first steps beyond Earth had already been taken. Humans had walked on the moon. Robotic spacecraft had visited Venus and Mars, and the inner solar system was beginning to feel familiar. Yet beyond the orbit of Mars lay a vast, largely unexplored region, dominated by giant planets whose true nature remained mostly unknown. Jupiter, Saturn, Uranus, and Neptune were visible from Earth, but they were still worlds of speculation, glimpsed only through telescopes and interpreted through theory rather than experience. It was during this moment of transition that the idea for the Voyager missions began to take shape. What made this period unique was not just technological readiness, but timing. Astronomers had identified a rare alignment of the outer planets that occurs only once every 176 years. During this alignment, the giant planets are positioned in such a way that a spacecraft can use their gravity sequentially, passing from one to the next with minimal fuel. This technique, known as gravity assist, allows a spacecraft to steal a small amount of orbital energy from a planet, increasing its speed and altering its direction. With careful planning, a single spacecraft could potentially visit multiple planets on one continuous journey. This opportunity would not return for generations. The scientific community recognized that this alignment offered something extraordinary, a chance to explore the outer solar system in a way that might never be possible again within a human lifetime. But the risks were immense. The distances were vast. Communication delays would stretch to hours. Repairs would be impossible. Instruments would have to survive intense radiation, extreme cold, and decades of operation. No spacecraft had ever been asked to endure such conditions. If a mission was to attempt this journey, it would need to be designed not for a few years, but for the unknown. From this realization emerged the Voyager program. The original vision was ambitious even by today's standards. Send robotic explorers to Jupiter and Saturn, and, if possible, onward to Uranus and Neptune. The spacecraft would carry a full suite of scientific instruments capable of studying atmospheres, magnetic fields, rings, moons, and the space between planets. they would also serve as test cases for long-duration deep space flight, pushing the limits of autonomy, reliability, and communication. Crucially, mission planners decided that one spacecraft would not be enough. The risks were too great, and the scientific return too important. A single failure could erase decades of planning. By launching 2 spacecraft on slightly different trajectories, scientists could increase the chances of success while also gathering complementary data. The 2 Voyagers would see the same planets from different angles and at different times, allowing comparisons that would deepen understanding rather than simply repeat observations. Voyager 2 was conceived as the long-path explorer. While its twin would take a faster route optimized for early arrivals, Voyager 2 was assigned a more complex and more demanding trajectory. Its mission was designed to preserve the possibility of continuing beyond Saturn, keeping the door open to Uranus and Neptune if the spacecraft survived the earlier encounters. This made Voyager 2, from the very beginning, a mission built around patience, endurance, and long-term vision. The scientific goals driving Voyager 2 were broad and fundamental. Scientists wanted to understand how giant planets form and evolve, how their atmospheres behave under extreme conditions, and how their magnetic fields interact with the surrounding space environment. They wanted to study moons, not as secondary objects, but as worlds in their own right, potentially shaped by internal heat, tidal forces, and complex chemistry. The outer solar system was seen not as a frozen, inactive region, but as a laboratory for understanding planetary systems everywhere. There was also a deeper motivation behind the mission, one less easily quantified. Voyager 2 represented a shift in how humanity approached exploration. Earlier missions had focused on specific destinations with defined endpoints. Voyager 2 was different. It was designed as a journey, not just a visit. Its planners knew that if it survived long enough, it would eventually leave the planetary region altogether and enter interstellar space. While this outcome was not the primary objective, it was acknowledged as a possibility and quietly embraced. The political and cultural context of the time also played a role. The Apollo era was drawing to a close, and public attention towards space exploration was beginning to wane. Voyager 2 was not a spectacle-driven mission. It offered no astronauts, no live broadcasts, no immediate drama. Instead, it promised a slow unfolding of discovery, measured in years rather than moments. In many ways, it was a leap of faith that curiosity alone could justify sustained exploration. Designing Voyager 2 required anticipating problems that could not yet be fully imagined. Engineers had to assume that systems would fail and build redundancy wherever possible. Computers had to be reliable, but simple enough to function for decades. Instruments had to be sensitive yet durable. Power had to be steady and independent of sunlight, leading to the choice of nuclear energy. Every decision was shaped by the understanding that Voyager 2 would be alone, far beyond the reach of human intervention. The decision to include a message from Earth was also made during this early phase. The Golden Record was not intended as a practical communication device, but as a symbolic gesture. It carried sounds, images, and music representing life on Earth, meant not for any specific recipient, but for the possibility of encounter in a distant future. including it reflected a quiet optimism. That exploration was not only about data, but about connection across space and time. When Voyager 2 was approved, it was done with an awareness that its full significance might not be understood for decades. The mission should unfold slowly, revealing its value over time, rather than all at once. Scientists and engineers accepted that many of those who worked on its launch would not be present to see its later achievements. Voyager 2 was, in this sense, a mission designed to outlive its creators. At its core, Voyager 2 was launched because humanity recognized a fleeting opportunity and chose not to ignore it. The alignment of the planets, the maturity of technology, and the depth of unanswered questions converged briefly. Voyager 2 became the embodiment of that moment, a machine built to move patiently through space, gathering knowledge without urgency, guided by physics rather than force. This chapter of the story begins not with launch, but with intention. Voyager 2 exists because a generation decided that some journeys are worth starting, even if their ending cannot be fully witnessed. The spacecraft was built to go farther than any before it, not in pursuit of conquest or profit, but in service of understanding. With its purpose defined and its path imagined, Voyager 2 was prepared for departure. The long journey outward had not yet begun, but the decision to send it had already set events in motion that would echo far beyond the limits of the solar system. Designing Voyager 2 required engineers to think beyond every previous space mission. This was not a spacecraft intended to operate for months or even a few years. It was designed to survive decades in an environment no human-made object had ever fully experienced. From the very beginning, the engineers understood that Voyager 2 would travel farther than any probe before it, through regions of space where sunlight was weak, temperatures were extreme, radiation was intense, and communication delays would make real-time control impossible. Every design decision was shaped by the assumption that the spacecraft would be alone, unsupported, and largely autonomous for most of its existence. One of the most fundamental challenges was power. Solar panels, which worked well near Earth and Mars, were useless in the outer solar system. Beyond Jupiter, sunlight is too faint to provide meaningful energy. Voyager 2 therefore relied on radioisotope power, using heat generated by the natural decay of plutonium to produce electricity. This power source was chosen not for efficiency, but for reliability. It provided a steady, predictable decline in output over time, allowing engineers to plan for gradual power loss rather than sudden failure. From the start, the mission accepted that instruments would need to be turned off one by one as energy diminished, extending the spacecraft's life through careful prioritization. The onboard computers reflected similar thinking. Voyager 2 carried multiple computers, each responsible for a different aspect of operation: command execution, attitude control, and data handling. These computers were extremely limited by modern standards, but they were designed to be robust and understandable. Their simplicity was a strength. Engineers could predict how they would behave under stress, radiation, and long periods of uninterrupted operation. Redundancy was built in wherever possible, allowing one system to take over if another failed. This was essential because no repairs would ever be possible once Voyager 2 left Earth. Communication posed another immense challenge. Voyager 2 needed to transmit data across billions of kilometers using very limited power. To accomplish this, it carried a large high-gain antenna capable of focusing radio signals into a narrow beam aimed back toward Earth. Maintaining this alignment required precise attitude control, even as the spacecraft slowly rotated to manage temperature. The deep space network on Earth, with its massive radio dishes spread across the globe, was built in part to support missions like Voyager 2. Even so, data rates would decrease dramatically with distance, turning communication into a slow, patient exchange measured in bits rather than streams. Voyager 2's scientific instruments were selected with versatility in mind. They had to study planets, moons, rings, magnetic fields, particles, and plasma, all using a limited payload. Each instrument was designed to operate independently, with its own power and data handling needs. Cameras were optimized for low light. Spectrometers were built to analyze atmospheric composition from afar. Particle detectors were shielded to survive intense radiation environments near Jupiter and Saturn. Together, these instruments formed a balanced toolkit capable of adapting to discoveries that could not yet be predicted. Thermal control was another silent but critical concern. In the cold of deep space, electronics can fail just as easily as they can overheat near the sun. Voyager 2 used a combination of insulation, heaters, and careful orientation to maintain stable internal temperatures. The spacecraft's slow rotation helped distribute heat evenly, preventing localized extremes. These systems had to function without intervention, responding passively to changing conditions as Voyager moved farther from the sun. Radiation posed a constant threat, especially during planetary flybys. Jupiter's radiation belts were known to be intense, but their true strength was uncertain before arrival. Voyager 2's electronics were shielded as much as possible, but complete protection was impossible. Engineers accepted that some components might degrade over time. The goal was not perfection, but resilience, the ability to continue operating even as individual parts aged or weakened. Autonomy became increasingly important as communication delays grew. Commands sent from Earth could take hours to reach Voyager 2, and responses would take just as long to return. This meant the spacecraft had to execute long sequences of instructions on its own, handling routine operations and minor anomalies without immediate guidance. Engineers developed a philosophy of cautious autonomy, limiting complexity while ensuring the spacecraft could protect itself if something unexpected occurred. Embedded within this highly practical machine was one element that served no operational purpose at all: the golden record. Mounted to the side of Voyager 2, it carried sounds, images, and music from Earth, along with instructions for playback. Its inclusion reflected a broader perspective on exploration. Voyager 2 was not only a scientific instrument, but also a cultural artifact, carrying evidence of its origin into interstellar space. The golden record acknowledged that Voyager 2 might one day outlast the civilization that created it. Every aspect of Voyager 2's design reflected restraint. Nothing was included unless it served a clear purpose. Nothing was assumed to be replaceable. Weight, power, and complexity were all limited deliberately. This discipline allowed the spacecraft to remain functional, far longer than originally expected. Voyager 2 was not built to be impressive in the moment, but to endure quietly over time. As construction neared completion, engineers tested Voyager 2 relentlessly. Systems were run continuously. Simulated failures were introduced. The spacecraft was exposed to vibration, vacuum, and temperature extremes. These tests could not replicate decades in space, but they revealed weaknesses that could be corrected before launch. By the time Voyager 2 was declared ready, it represented one of the most thoroughly tested machines ever built. Voyager 2 emerged from this process not as a fragile probe, but as a patient traveler. It was designed to move steadily through space, gathering data without urgency, responding predictably to known challenges, and tolerating the unknown. Its strength lay not in speed or power, but in balance, a careful alignment of simplicity, redundancy, and foresight. With its systems finalized and its purpose clear, Voyager 2 was prepared for launch. The machine built to explore the outer solar system now awaited the moment when intention would turn into motion, and planning would give way to trajectory. Voyager 2's journey began not with motion, but with commitment. By the time the spacecraft was placed atop its launch vehicle in the summer of 1977, years of planning, debate, and design had already shaped every detail of its future. Unlike missions with short timelines and nearby destinations, Voyager 2 was intended to leave Earth permanently, carrying its momentum and purpose far beyond any possibility of return. Launch day was not the start of exploration, but the point of no reversal. Voyager 2 lifted off on August 20th, 1977, launched aboard the Titan IIIe Centaur launch vehicle. This rocket was chosen not for spectacle, but for capability. It was one of the few systems powerful and precise enough to send a spacecraft directly onto an interplanetary trajectory. The Titan stages provided the raw thrust needed to escape Earth's gravity, while the Centaur upper stage performed the delicate task of injecting Voyager 2 into its carefully calculated solar orbit. The success of this final burn mattered more than everything that came before it, because it determined whether the spacecraft would ever reach the outer planets at all. The launch sequence unfolded over minutes, but its consequences would last decades. As the rocket climbed through the atmosphere, Voyager 2 experienced intense vibration, acceleration, and stress. These conditions were among the most violent the spacecraft would ever face. Once the Centaur completed its burn, and Voyager 2 separated cleanly, the violence ended abruptly. The spacecraft entered the quiet of space, carrying with it a speed far greater than any aircraft or satellite before it. From that moment onward, Voyager 2 was no longer supported by thrust. It was sustained by inertia. At separation, Voyager 2 was already traveling at tens of thousands of kilometers per hour relative to Earth. This initial velocity was not its final speed, but it was enough to place the spacecraft on a solar orbit that would carry it outward toward Jupiter. Unlike later stages of the mission, no gravity assists had yet been applied. Voyager 2's speed at this point came almost entirely from the energy imparted by the launch vehicle and the careful shaping of its trajectory. Every kilometer per second mattered, because there would be no opportunity to correct large errors later. Shortly after launch, Voyager 2 entered a critical commissioning phase. Engineers verified that its antenna could point accurately toward Earth, that its computers were functioning correctly, and that its instruments responded as expected. Communication delays were already noticeable, measured in minutes rather than seconds. Commands had to be planned, transmitted, and executed without immediate feedback. This was the first test of Voyager 2's autonomy, and it set the tone for everything that followed. Voyager 2's early trajectory was intentionally conservative. Mission planners needed to preserve flexibility for later planetary encounters, especially Saturn, Uranus, and Neptune. This meant avoiding aggressive maneuvers early on that could compromise timing or geometry. The spacecraft followed a smooth, gradual arc away from Earth, remaining well within the Sun's gravitational control while accumulating distance steadily. Its speed relative to the Sun stabilized at a level that would carry it efficiently toward Jupiter without exhausting navigational margins. One of the most subtle challenges during this phase was orientation. Voyager 2 needed to balance several competing requirements, keeping its high-gain antenna pointed toward Earth, maintaining thermal stability, and positioning its instruments appropriately for calibration. Small thrusters adjusted the spacecraft's attitude gently and infrequently, conserving fuel that would be needed decades later. Each adjustment was deliberate, planned with the understanding that even small inefficiencies could matter over long timescales. As days turned into weeks, Voyager 2 crossed the orbit of the Moon, then the orbit of Mars, leaving behind regions of space that had once defined the limits of exploration. The spacecraft passed through the asteroid belt without incident, confirming that this vast region was far emptier than early science fiction had imagined. Instruments recorded dust impacts and particle counts, contributing to a clearer picture of interplanetary space. These measurements, though not dramatic, helped refine models of how matter is distributed throughout the solar system. Throughout this early journey, Voyager 2's speed continued to be shaped primarily by gravity rather than propulsion. The spacecraft did not accelerate in the conventional sense. Instead, it conserved the energy it already had, coasting smoothly through space. Relative to the Sun, its velocity remained high and stable, setting the stage for the first major transformation of the mission at Jupiter. The spacecraft was moving fast enough that, once gravity assists were applied, escape from the planetary region would become inevitable. Psychologically, the launch marked a profound shift for the mission team. Voyager 2 was now unreachable. Unlike missions in Earth orbit, there would be no servicing, no rescue, no correction through direct intervention. Every success and every failure would unfold at a distance, mediated by radio signals traveling at the speed of light. This reality demanded a different relationship between humans and machine, one based on trust rather than control. The fact that Voyager 2 launched before Voyager 1 was not a coincidence. Its trajectory required an earlier departure to align correctly with Jupiter and Saturn, while preserving the option to continue onward. Voyager 2's mission was the more ambitious of the two, and its early launch reflected the complexity of its path. From the very beginning, it carried the responsibility of going farther, staying longer, and enduring more. As Voyager 2 settled into its cruise phase, the launch faded into memory. The rocket that carried it upward fell away, its role complete. What remained was a small, quiet spacecraft moving steadily outward, guided by physics and foresight rather than force. The violence of launch gave way to the patience of travel, and the mission entered a rhythm that would persist for decades. This chapter of Voyager 2's story is not about spectacle, but about transition. Launch transformed intention into motion, and planning into trajectory. The spacecraft was now committed to its path, carrying with it the accumulated decisions of countless engineers and scientists. The outward journey had begun, not with urgency, but with resolve. As Voyager 2 continued away from Earth, it carried its speed, its systems, and its purpose intact. Ahead lay Jupiter, the first giant, where gravity would reshape the mission and accelerate the spacecraft into a new phase of exploration. Behind it lay Earth, growing smaller with every passing hour, already beyond the reach of return. The launch was brief. The journey it enabled would last longer than any human mission before it, unfolding slowly and quietly through the vast spaces between worlds. After launch and early commissioning, Voyager 2 settled into the long, outward passage through the inner solar system, a phase that seems quiet only because nothing happens in the cinematic sense. In reality, this cruise was an extended engineering performance where the spacecraft had to remain healthy, stable, and precisely guided while distance accumulated relentlessly. Voyager 2 was already moving at interplanetary speed, but the essential question was not how fast it was going. It was whether it would arrive at Jupiter with the correct geometry. A gravity assist is not something you can improvise at the last moment, because it depends on arriving at a specific point in space, at a specific time, with a specific approach angle. That required patience, measurement, and restraint, all practiced continuously while the spacecraft traveled through a region that still felt, in solar terms, close to home. The first major task of the inner cruise was to prove reliability under real conditions. Voyager 2's computers, sensors, and radio system were tested not as isolated components, but as a living system, operating together. The spacecraft had to maintain a stable orientation so that its high-gain antenna stayed pointed toward Earth, because communication was no longer optional. Telemetry was the mission's heartbeat, returning measurements about temperatures, voltages, currents, and the health of subsystems. At the same time, Voyager 2 had to manage thermal balance. In deep space, you cannot cool by airflow, and you cannot warm by friction. Temperature is controlled by internal power, insulation, heaters, and how the spacecraft presents itself to sunlight. A small change in orientation could change the thermal environment of instruments, and over long timescales, small thermal stresses can matter. So the spacecraft's attitude, its steady pointing, became a form of long-duration discipline. Hold the antenna on Earth, keep the body stable, keep the instruments within safe ranges, and do it day after day. Navigation during the cruise was a constant act of listening. The Deep Space Network transmitted a radio tone. Voyager 2 returned it, and engineers measured minute frequency shifts caused by motion, using the Doppler effect as a precise tool for determining velocity along the line of sight. By combining these measurements with accurate models of Earth's motion, the spacecraft's predicted trajectory, and the known gravitational influences of the Sun and planets, navigators could estimate where Voyager 2 was headed with remarkable accuracy. When they found a drift, they did not rush to correct it. They waited until the correction was worth the fuel and worth the risk. Small thruster burns were used not to speed up, but to refine direction, turning a tiny change in velocity into a large change in future position. This is one of the most counterintuitive truths of interplanetary flight. A fraction of a meter per second, applied early, can shift the aim point at a giant planet by thousands of kilometers. While navigation refined the path, the science instruments began to build the mission's first continuous portrait of space itself. Even before encountering Jupiter, Voyager 2 could measure the solar wind, the stream of charged particles flowing outward from the sun. This wind is not uniform. It arrives in fast streams and slow streams, compressions and rarefactions, shaped by the sun's rotating magnetic field and by eruptions from the solar surface. Instruments recorded variations in particle density, speed, and energy, allowing scientists to connect changes at the spacecraft with events that had occurred at the sun days earlier. The magnetic field instrument mapped the structure of the sun's field as it is carried outward, showing the spiral geometry created by the sun's rotation. These measurements were not merely background noise. They were the beginning of a second mission, woven into the first. Understanding the heliosphere, the bubble of solar influence that fills the solar system. The inner solar system cruise also required a careful relationship with time. Communication delays were still measured in minutes rather than hours, but they were long enough to make real-time control unrealistic. Mission operations became a sequence of planned events rather than reactive steering. Commands were assembled into blocks, verified, transmitted, then executed later by the spacecraft. When data returned, it came as confirmation, not as a live conversation. This gradually reshaped how the team worked. They became more like authors writing instructions for a distant machine than pilots flying it. They planned with margins. They expected uncertainty. They built sequences that would remain safe, even if a measurement was slightly off or a timing was slightly shifted. As distance grew, the mission learned to move at the speed of careful thought rather than the speed of urgency. Crossing the asteroid belt is often imagined as a dangerous obstacle course, but the reality is calmer and more interesting. The asteroid belt is enormous, and it is mostly empty space. Voyager 2 did not fly between close rocks like a ship through debris. Individual asteroids are separated by vast distances, and the probability of collision is extremely low. Still, the belt is meaningful scientifically because it contains a long-lived population of small bodies and dust. Voyager 2 could register tiny dust impacts and changes in particle populations, contributing to a clearer understanding of how fine material is distributed between planets. Even a single dust grain at interplanetary speeds carries energy, and over decades, these impacts slowly weather surfaces. Measuring dust is a way of measuring the slow abrasion of space. As Voyager 2 continued outward, sunlight weakened. This did not change the spacecraft's power system, because electricity came from radioisotope generators, but it did change the environment. Thermal conditions shifted subtly. Imaging conditions shifted as the brightness of targets changed and the sun's glare diminished. The sky itself remained star-filled, yet the way instruments perceived it depended on background light and noise. Meanwhile, cosmic rays from beyond the solar system were always present, and as the spacecraft moved outward, the balance between solar particles and galactic particles began to shift slowly. This was not yet the dramatic rise seen near the heliopause, but it was the beginning of a trend. The farther Voyager 2 traveled, the less the sun's wind dominated the local radiation environment. One of the most important hidden achievements of the cruise phase was the development of operational confidence. A spacecraft that is going to survive Jupiter and then continue for decades cannot be treated as a fragile object that must be constantly handled. It must be treated as a stable system that can be trusted to do routine things correctly. The team learned how Voyager 2 behaved when heaters cycled, when instruments switched on, when the antenna repositioned, when the spacecraft adjusted its attitude. They learned its rhythms. They learned the subtle signatures that indicated normal behavior and the subtle signatures that suggested trouble. This kind of familiarity is difficult to create, and it can only be earned over time. By the time Voyager 2 neared Jupiter, the mission team did not merely know the spacecraft's specifications. They knew its personality as a system. Throughout this cruise, the logic of the entire mission remained in the background like a steady drumbeat. Voyager 2 was not simply traveling toward Jupiter to look at it. It was traveling toward Jupiter to use it. Jupiter would provide the first major gravitational slingshot, increasing Voyager 2's speed and bending its path toward Saturn, and potentially beyond. That future depended on arriving correctly now. The approach angle would decide where the spacecraft passed, relative to Jupiter's motion around the Sun, and therefore how much energy could be transferred. In a gravity assist, the spacecraft's speed relative to the planet changes dramatically as it falls into and climbs out of the planet's gravity well. But the deeper purpose is the change in speed relative to the Sun, which can increase without any engine burn. This is one of the most elegant tricks in spaceflight. You borrow momentum from a planet's orbital motion, and in doing so, you write the next chapter of your trajectory. As the cruise continued, planning for Jupiter became increasingly detailed. Scientists and engineers had to decide what success would look like when the spacecraft finally arrived. Imaging sequences needed exposure settings, scan rates, and pointing schedules. Instruments that measured particles and magnetic fields needed continuous operation through key regions. Some measurements required the antenna to point away from Earth temporarily to aim instruments or cameras, which meant accepting short pauses or reduced rates of communication. All of this had to be coordinated as a single choreography because the spacecraft could not point everywhere at once. Trade-offs were inevitable. A moment spent taking a high-resolution image might be a moment when another instrument was not ideally oriented. And yet, the goal was not perfection. The goal was an intelligently chosen balance that would capture the most valuable data across many categories, because Jupiter is not one phenomenon. It is an atmosphere, a magnetosphere, a radiation environment, and a system of moons. As Jupiter gradually brightened in the instruments, the inner cruise began to feel like an approach rather than a passage. The spacecraft's trajectory had been refined. Its systems had been tested. Its operational routines had become reliable. Communication delays were longer. The data rates were a little lower, and Earth was a little smaller behind it. But Voyager 2 remained steady, stable, and purposeful, carrying forward the accumulated energy of launch and the careful adjustments of navigation. The mission was still quiet, but now the quiet had direction. By the end of this phase, Voyager 2 was no longer simply on the way. It was on a path that was about to become irreversible in a new way. Jupiter was approaching, and with it came an environment unlike anything the spacecraft had experienced. Stronger magnetic fields, denser particle populations, and radiation levels capable of stressing electronics and instruments. The cruise phase had prepared Voyager 2 not just to arrive at Jupiter, but to survive it, and then to continue onward with enough stability to make Saturn, Uranus, and Neptune possible in the first place. Voyager 2 continued outward, calm and unhurried, carrying the outer solar system ahead of it like a promise, and Earth behind it like a fading reference point. And the long cruise through the inner solar system completed its purpose. It delivered a small machine, intact and ready, to the threshold of its first giant world. When Voyager 2 approached Jupiter in the summer of 1979, it entered an environment unlike anything encountered during its long cruise through the inner solar system. Jupiter is not merely the largest planet. It is a dominant system unto itself, exerting immense gravitational, magnetic, and radiative influence over a vast region of space. Long before Voyager 2 came close enough to resolve the planet in detail, its instruments detected rising particle densities and increasingly intense radiation, signaling that the spacecraft was crossing into Jupiter's domain. As Jupiter grew from a bright disk into a richly detailed world, Voyager 2's cameras revealed an atmosphere in constant motion. Bands of clouds wrapped around the planet, driven by powerful jet streams flowing in alternating directions. These winds reached speeds far exceeding those found on Earth, sustained not by sunlight alone, but by heat rising from deep within the planet. Voyager 2 confirmed that Jupiter radiates more energy than it receives from the Sun, reshaping scientific understanding of how giant planets function. Jupiter was not passive. It was internally active, fueled by residual heat from its formation. The Great Red Spot dominated the visual record, a vast storm system larger than Earth itself. Voyager 2's images showed its intricate internal structure, revealing swirling motions, sharp boundaries, and interactions with surrounding cloud bands. These observations demonstrated that Jupiter's storms are not temporary features, but long-lived systems maintained by the planet's rapid rotation and deep atmospheric dynamics. The data collected here helped establish that weather on gas giants follows rules fundamentally different from those governing terrestrial climates. Voyager 2's encounter with Jupiter transformed understanding of planetary magnetism. The spacecraft measured a magnetic field far stronger than Earth's, extending millions of kilometers into space. This field trapped charged particles, creating radiation belts that were intense enough to pose a serious threat to spacecraft electronics. Voyager 2 passed through these regions carefully, its instruments recording particle energies that exceeded previous estimates. The data revealed that Jupiter's magnetic field is generated by motion within a deep layer of metallic hydrogen, a state of matter that exists only under extreme pressure. The moons of Jupiter proved to be among the most significant discoveries of the mission. Io, the innermost large moon, displayed active volcanism, with plumes of material erupting hundreds of kilometers above its surface. Voyager 2's observations confirmed that these eruptions were driven by tidal heating, caused by gravitational interactions with Jupiter and neighboring moons. This discovery demonstrated that geological activity could be sustained without sunlight or radioactive decay, expanding the definition of what makes a world active. Europa appeared smooth and bright, crisscrossed by dark lines, and largely free of impact craters. Voyager 2's images suggested that its surface was young and dynamic, possibly underlain by a subsurface ocean beneath an icy crust. Although Voyager 2 could not confirm the presence of liquid water directly, the visual evidence pointed toward internal processes reshaping the moon from below. This made Europa one of the most compelling candidates for future exploration in the search for environments that could support life. Ganymede and Callisto presented contrasting histories. Ganymede showed signs of ancient tectonic activity, with grooved terrain indicating internal differentiation and structural evolution. Callisto, heavily cratered and largely unchanged, appeared to preserve a record of early solar system impacts. Together, these moons illustrated the diversity of outcomes possible within a single planetary system, shaped by gravity, composition, and time. Throughout the encounter, Voyager 2's trajectory was shaped by Jupiter's gravity. As the spacecraft passed behind the planet, relative to its motion around the Sun, it experienced a gravitational assist that increased its heliocentric speed and redirected its path toward Saturn. This maneuver required no fuel. Instead, it relied on precise timing and geometry, allowing Voyager 2 to borrow energy from Jupiter's orbital motion. The result was a significant increase in outward velocity, committing the spacecraft more firmly to its long journey through the outer solar system. The Jupiter flyby also tested Voyager 2's resilience. Radiation levels stressed electronics. Particle impacts and electromagnetic noise challenged instruments. Yet the spacecraft continued to operate within expectations, confirming that its design choices had been sound. Data flowed back to Earth at a steady pace, despite increasing communication delays, and scientists began the long process of interpreting results that would occupy them for decades. As Voyager 2 departed Jupiter, the planet gradually receded behind it, shrinking once again into a point of light. The spacecraft emerged from the most intense radiation environment it had yet encountered, carrying with it a transformed understanding of giant planets and their moons. Jupiter had not merely been observed, it had reshaped the mission, increasing Voyager 2's speed and redefining what planetary systems could be. The encounter marked a turning point. Voyager 2 was no longer simply on its way to the outer planets. it had proven that the grand tour was possible. With Jupiter behind it and Saturn ahead, the mission moved forward with renewed confidence, carrying the first giant's lessons into the deeper reaches of the solar system. When Voyager 2 approached Saturn in the early 1980s, the mission entered its most delicate and consequential phase. Jupiter had proven that the spacecraft could survive a giant planet encounter. But Saturn represented something far more complex than another destination. It was the point where the future of the mission would be decided. Every choice made during this encounter would determine whether Voyager 2 would continue onward to Uranus and Neptune, or become, like many missions before it, a visitor that turned back inward after completing its primary objectives. Saturn was not just a world to be studied, it was a crossroads. From a distance, Saturn announced itself through subtle changes in the surrounding space environment. Voyager 2's instruments detected shifts in particle populations and magnetic field structure long before the planet filled the camera frame. Compared to Jupiter, Saturn's magnetosphere was gentler, but broader and more orderly. Its magnetic field showed a remarkable alignment with the planet's rotation axis, a near-perfect symmetry that puzzled scientists. This unexpected regularity suggested a different internal structure and dynamo process from Jupiter's, challenging existing theories about how planetary magnetic fields are generated. As Voyager 2 drew closer, Saturn's rings emerged as one of the most visually striking structures ever observed. From Earth, the rings appeared smooth and continuous. Voyager 2 revealed them as a finely detailed system composed of countless individual ringlets, gaps, waves, and resonances. Gravitational interactions with Saturn's moons shaped the rings constantly, creating ripples that propagated through the material, like patterns in a flowing river. These observations transform the rings from static ornaments into dynamic systems governed by ongoing physical processes. Saturn's atmosphere, though less turbulent in appearance than Jupiter's, revealed its own complexity. Voyager 2 measured high-speed winds flowing around the planet, driven by internal heat rather than solar energy alone. Temperature profiles showed layered structures, with energy moving upward from deep within the planet. Like Jupiter, Saturn radiated more heat than it received from the Sun, confirming that giant planets remain thermally active long after their formation. Saturn was not a frozen relic. It was a living system, slowly evolving over immense timescales. The moons of Saturn added another layer of significance to the encounter. Titan, the largest moon, was of particular importance. Its thick atmosphere made it unique among moons in the solar system, and understanding its composition was a high scientific priority. Voyager 2 flew at a distance that allowed detailed atmospheric measurements while preserving the mission's onward trajectory. Instruments confirmed that Titan's atmosphere was dominated by nitrogen, with complex organic molecules present in trace amounts. Although the surface remained hidden beneath dense haze, the data suggested active chemistry occurring high above the ground, hinting at processes that could resemble early conditions on Earth. Other moons told different stories. Mimas displayed a massive impact crater that nearly fractured the moon entirely, revealing how close small bodies can come to destruction without fully breaking apart. Enceladus appeared unusually bright, its icy surface reflecting sunlight efficiently. Although Voyager 2 could not yet detect the subsurface ocean known today, its observations hinted that Enceladus was not entirely inactive. Each moon contributed to a broader understanding of how diverse and dynamic satellite systems can be around giant planets. Throughout the Saturn encounter, Voyager 2's path was guided with extraordinary precision. The spacecraft approached the planet at an angle chosen not only for science, but for destiny. By passing behind Saturn relative to its motion around the Sun, Voyager 2 was able to use the planet's gravity to reshape its trajectory. This gravitational assist did not merely increase speed, it redirected the spacecraft's path in a way that preserved the possibility of reaching Uranus. Unlike Voyager 1, which had sacrificed future encounters for a close Titan flyby, Voyager 2's trajectory was designed to keep the Grand Tour alive. This difference marked the critical decision of the mission. Voyager 2 would not take the shortest or simplest path. It would take the harder one. The flyby geometry was carefully balanced to collect meaningful data while maintaining the precise exit angle needed for the long journey ahead. Saturn's gravity provided a powerful but unforgiving tool. A small error in timing or distance could have ended the mission's planetary phase entirely. Instead, the spacecraft emerged from the encounter with its course intact and its future open. The gravity assist at Saturn increased Voyager 2's heliocentric speed further, locking in the energy needed to carry it toward Uranus. From this point on, returning inward toward the Sun was no longer possible. The spacecraft's momentum and direction committed it fully to the outer solar system. Saturn did not end the mission. It extended it, transforming Voyager 2 from a planetary explorer into a traveler toward worlds never before visited. Communication delays grew longer during this phase, and operational autonomy became even more important. Voyager 2 executed complex observation sequences on its own, storing data and transmitting it slowly back to Earth. The mission team could not intervene in real time. They could only wait, listen, and trust the systems they had built years earlier. Each successful transmission reinforced confidence that Voyager 2 could endure the increasing isolation ahead. As Voyager 2 departed Saturn, the planet and its rings receded into the distance, their influence fading gradually rather than abruptly. The spacecraft moved back into quieter interplanetary space, but now with a very different trajectory from before. Saturn lay behind it, not as a conclusion, but as a gateway. Ahead waited Uranus, a planet no spacecraft had ever visited, reachable only because Saturn's gravity had been used with extraordinary care. The Saturn encounter marked the moment when Voyager 2 truly separated itself from all previous planetary missions. It was no longer following a known path or repeating familiar exploration. It was advancing into territory where no precedents existed, carrying with it the accumulated knowledge of Jupiter and Saturn, and the momentum needed to go farther still. By the end of this chapter, Voyager 2 was no longer defined by what it had already seen, but by what it was now capable of reaching. Saturn had tested the mission's patience, precision, and restraint. and Voyager 2 had passed. The spacecraft continued onward, steady and unhurried, carrying the promise of new worlds ahead and the certainty that every decision from here on would echo across decades of travel. When Voyager 2 approached Uranus in the mid-1980s, it carried with it the weight of something unprecedented. No spacecraft had ever visited this planet before. Everything known about Uranus came from distant observations made from Earth, filtered through atmosphere and limited by resolution. Voyager 2 was not refining existing knowledge. It was creating it from nothing. The encounter represented humanity's first and only close look at a world fundamentally unlike any previously explored. Uranus is a planet defined by extremes that are not immediately obvious. From afar, it appears calm and featureless, a pale blue-green disk with little visible structure. Yet Voyager 2 revealed that this apparent simplicity hides a deeply unusual planetary system. Uranus rotates on its side, tilted by approximately 98 degrees relative to its orbit. This extreme tilt means that its poles experience decades of continuous sunlight, followed by decades of darkness. Voyager 2 arrived when one pole was facing almost directly toward the sun, presenting a configuration no telescope on Earth could fully interpret. As Voyager 2 drew closer, its instruments began to map Uranus's atmosphere in detail. The planet's blue-green color was confirmed to result from methane gas, absorbing red light while reflecting blue wavelengths. Beneath this simple explanation lay a complex atmospheric structure. Voyager 2 measured wind speeds reaching hundreds of kilometers per hour, flowing in unexpected directions relative to the planet's rotation. Unlike Jupiter and Saturn, Uranus showed fewer visible cloud bands, but this did not mean inactivity. The planet's atmosphere was dynamically restrained rather than chaotic, shaped by low internal heat and extreme axial tilt. One of the most surprising discoveries involved Uranus's magnetic field. Voyager 2 found that the planet's magnetic axis was tilted significantly relative to its rotation axis and offset from the planet's center. This created a highly asymmetric magnetosphere that twisted and reconfigured itself as Uranus rotated. Charged particles moved through this field in complex patterns, producing magnetic behavior, unlike that seen at any other planet. This discovery forced scientists to reconsider how planetary magnetic fields can arise and how deeply they are tied to internal structure. Uranus's ring system, previously thought to be minimal, revealed unexpected complexity. Voyager 2 detected multiple narrow rings, dark and sharply defined, composed of material that reflected very little light. These rings were not broad and bright like Saturn's, but thin and constrained, suggesting strong gravitational shepherding by nearby moons. Their existence hinted at a dynamic balance between collisions, aggregation, and gravitational control that maintained their structure over time. The moons of Uranus were another revelation. Voyager 2 discovered several new moons and closely studied those already known. These moons displayed a range of surface features, from heavily cratered terrains to signs of tectonic activity. Miranda, one of the smallest moons, was particularly striking. Its surface appeared fractured and reassembled, with enormous cliffs, ridges, and mismatched terrain blocks. This chaotic appearance suggested a violent geological history, possibly involving partial disruption and reformation. Voyager Two's images of Miranda challenged assumptions about how small moons evolve and survive. Throughout the Uranus encounter, Voyager Two's trajectory had to be executed with extraordinary care. The spacecraft passed close enough to gather detailed data, while maintaining the precise exit path needed for the next stage of the mission. Uranus's gravity provided another crucial assist, increasing Voyager 2's heliocentric speed and bending its trajectory toward Neptune. This maneuver further committed the spacecraft to the outermost reaches of the solar system. With each gravity assist, Voyager 2 became faster and less bound to the Sun, converting planetary motion into outward momentum. The data Voyager 2 collected at Uranus fundamentally reshaped planetary science. Uranus could no longer be treated as a simple ice giant, similar to Neptune. Its extreme tilt, unusual magnetic field, and subdued atmospheric activity set it apart as a category of its own. These findings also had implications beyond the solar system. As astronomers began discovering exoplanets, many with extreme tilts or unusual orbital configurations, Uranus became a key reference point for understanding how planetary systems can form and evolve in unexpected ways. Communication during the Uranus encounter tested the limits of mission operations. Voyager 2 was now so distant that commands and responses were separated by many hours. Observation sequences were executed autonomously, with Earth receiving confirmation long after events had already passed. The spacecraft's ability to perform reliably without intervention validated decades-old engineering decisions and reinforced confidence that Voyager 2 could survive even greater distances. As Voyager 2 departed Uranus, the planet slowly receded into the background, returning to a faint disk and then a point of light. Behind it lay the first complete exploration of a planet never before visited. Ahead lay Neptune, the final giant, and the last opportunity for close planetary observation. Uranus had expanded humanity's understanding of what a planet could be, revealing that even the quietest-looking worlds can harbor profound complexity beneath their surfaces. By the end of this encounter, Voyager 2 had become something more than a planetary probe. It was now an emissary from the inner solar system to the distant frontier, carrying knowledge gathered from worlds of gas, ice, and rock. Uranus marked the point where exploration crossed fully into the unknown, not just in distance, but in understanding. When Voyager 2 approached Neptune in late 1989, it carried the distinction of being humanity's last visitor to a major planet for the foreseeable future. Unlike Jupiter, Saturn, or even Uranus, Neptune had remained almost entirely theoretical in character. Its existence had been inferred mathematically long before it was observed directly, and even by the time Voyager 2 arrived, it was still a world defined more by equations than by experience. The Neptune encounter was therefore not a continuation of exploration, but a culmination, the final unveiling of a planet that marked the outer boundary of classical planetary science. Neptune revealed itself first through motion rather than appearance. As Voyager 2 drew closer, instruments detected changes in the surrounding particle environment, indicating the growing influence of the planet's magnetosphere. Neptune's magnetic field, like Uranus's, was found to be highly tilted and offset from the planet's center. This unexpected similarity suggested that ice giants generate magnetic fields through mechanisms very different from those of gas giants like Jupiter and Saturn. The discovery forced scientists to consider that magnetic dynamos can arise in shells of conductive fluids rather than deep metallic cores, broadening the understanding of planetary interiors. Visually, Neptune was a study in contrast. Despite receiving far less sunlight than any planet previously visited, its atmosphere was extraordinarily active. Voyager 2's images revealed powerful storms, including a massive dark feature, later called the Great Dark Spot. Surrounding this storm were high-speed winds moving faster than any measured elsewhere in the solar system, reaching speeds of more than 2,000 kilometers per hour. These winds contradicted expectations because Neptune radiates relatively little internal heat compared to Jupiter or Saturn. Yet somehow, its atmosphere converted that energy into extreme motion, demonstrating that distance from the sun does not imply atmospheric quiet. Voyager 2's instruments showed that Neptune's deep blue color resulted from methane absorption, similar to Uranus, but the distribution of clouds and storms indicated a far more dynamic system. Bright methane ice clouds formed and dissipated rapidly, suggesting strong vertical convection. Temperature measurements revealed a complex atmospheric structure, with heat rising from the interior and interacting with solar input in unexpected ways. Neptune emerged not as a cold, inert giant, but as a planet of motion, driven by forces still not fully understood. Neptune's rings were another surprise. From Earth, they appeared faint and incomplete. Voyager 2 revealed them as narrow, clumpy structures composed of dark material. Some sections of the rings appeared brighter than others, forming arcs rather than continuous bands. These arcs suggested gravitational confinement by nearby moons, holding material in place against the tendency to spread out. This discovery showed that ring systems can exist in stable but highly structured forms, challenging assumptions based on Saturn's broad, uniform rings. The moons of Neptune added emotional weight to the encounter, particularly Triton. Voyager 2's flyby of Triton revealed a world unlike any other moon previously observed. Triton's surface was young and sparsely cratered, indicating recent geological activity. Even more astonishing were the geysers observed erupting from its surface, ejecting plumes of nitrogen gas and dark material into the thin atmosphere. These cryovolcanic eruptions demonstrated that even distant, frozen worlds can be internally active, reshaping ideas about where energy and motion can arise in the solar system. Triton's retrograde orbit also hinted at a dramatic past. Unlike most large moons, Triton orbits Neptune in the opposite direction of the planet's rotation, suggesting it was captured rather than formed in place. This capture would have disrupted Neptune's original moon system, possibly destroying or ejecting earlier satellites. Voyager 2's observations provided the first direct evidence of this violent history, turning Triton into a key example of how planetary systems can be rearranged long after formation. Throughout the Neptune encounter, Voyager 2's trajectory was managed with extreme care. This would be the final gravity assist of the mission. Neptune's gravity increased Voyager 2's heliocentric speed once more and redirected its path downward relative to the plane of the solar system. This maneuver marked the definitive end of the planetary phase. After Neptune, there would be no more close encounters, no more opportunities to reshape the mission's path using planetary motion. The spacecraft was now committed to leaving the realm of the planets entirely. Communication during the Neptune flyby was stretched to its limits. Signals took many hours to travel between Earth and Voyager 2, and data rates were extremely low. Observation sequences had been planned months in advance, leaving no room for improvisation. The spacecraft executed these sequences autonomously, recording images and measurements, while Earth waited patiently for confirmation. When the data finally arrived, it confirmed that Voyager 2 had completed the most ambitious planetary exploration ever attempted by a single spacecraft. As Voyager 2 departed Neptune, the planet quickly receded into darkness. The spacecraft moved away from the Sun's last major companion, carrying with it a complete first survey of the outer planets. Neptune was not just another data point. It was the closing chapter of an era that began with telescopic observation and ended with direct exploration. Beyond Neptune lay a region of space defined less by planets than by particles, fields, and gradual transitions. The solar system thinned outward into the heliosphere, where the sun's influence slowly weakened. Voyager 2 was no longer approaching destinations. It was entering a journey defined by distance rather than encounter. Neptune marked the edge of familiarity. Everything beyond it would be measured differently, not by images of worlds, but by changes in the environment itself. Voyager 2 continued onward, carrying the memory of blue storms, icy moons, and dark rings into a quieter, more abstract phase of its voyage. The last giant planet had been seen. The path ahead was open, unmarked, and vast. After Neptune, Voyager 2 entered a phase of its journey defined not by destinations, but by gradual transitions. The solar system does not end at a sharp boundary. There is no wall, no sudden drop into emptiness. Instead, the sun's influence fades slowly, expressed through changes in particles, magnetic fields, and pressure. Voyager 2 became an explorer of these invisible structures, moving outward through regions that cannot be photographed, but can be measured with patience and precision. At the heart of this phase is the heliosphere, a vast bubble carved into interstellar space by the solar wind. The sun continuously emits charged particles that stream outward in all directions, carrying the solar magnetic field with them. This flow creates a region where the sun dominates the local environment, pushing back against material drifting between the stars. For decades, the heliosphere had been theorized and modeled, but its actual structure remained uncertain. Voyager 2 was now positioned to transform those models into measurements. As the spacecraft moved farther from the sun, its instruments detected a gradual weakening of the solar wind. Particle densities decreased, and the magnetic field became less orderly. This was not a failure of the sun's influence, but a sign of competition. Interstellar particles, long held at bay, began to press inward. Voyager 2 was approaching the termination shock, the region where the solar wind slows abruptly as it begins to lose its dominance. Crossing the termination shock did not feel dramatic to the spacecraft. There was no jolt or sudden event. Instead, the instruments recorded changes in particle energies and flow directions, confirming that the solar wind had transitioned from supersonic to subsonic speeds. This was a milestone not because of spectacle, but because it confirmed decades of theoretical work. The sun's wind did not fade smoothly. It slowed, compressed, and became turbulent as it encountered resistance from the interstellar medium. Beyond the termination shock lies the heliosheath, a vast, chaotic region where solar and interstellar influences intermingle. Voyager 2 spent years traveling through this zone, recording fluctuations in particle populations and magnetic fields. The environment was variable and unpredictable. Particle intensities rose and fell. Magnetic field directions shifted. The heliosheath was not a quiet boundary layer, but a region of interaction, shaped by pressure, motion, and long-term change. One of the most valuable contributions Voyager 2 made during this phase was comparison. Because Voyager 1 and Voyager 2 followed different paths out of the solar system, their measurements revealed that the heliosphere is not symmetrical. Its shape is influenced by the direction of the interstellar magnetic field and by variations in solar activity over time. Voyager 2's data showed differences in shock location, particle behavior, and magnetic structure that could not be explained by distance alone. The heliosphere was revealed as a dynamic, evolving structure rather than a static bubble. As Voyager 2 continued outward, communication delays grew to extraordinary lengths. Signals took many hours to travel between Earth and the spacecraft. Data rates became extremely low, forcing scientists to choose carefully which instruments could remain active. Power from the radioisotope generators declined slowly as radioactive material decayed. Systems were shut down one by one, not because they failed, but to preserve energy for the most essential measurements. Voyager 2 became simpler over time, shedding capabilities while maintaining its core purpose: to measure the environment beyond the planets. Eventually, Voyager 2 reached the heliopause, the outer boundary of the heliosphere, where the pressure of the solar wind is balanced by the pressure of interstellar space. Crossing this boundary marked the moment when the spacecraft truly left the solar system's domain. Beyond the heliopause, the sun's particles no longer dominated. Voyager 2 entered interstellar space, a region defined not by planets or orbits, but by the diffuse matter between stars. In interstellar space, Voyager 2's instruments detected a higher density of galactic cosmic rays, particles accelerated by distant astrophysical events, such as supernovae. The magnetic field changed character, becoming steadier and aligned with a broader galactic environment, rather than the sun. These measurements provided the first direct sampling of interstellar conditions by a human-made object, transforming abstract concepts into tangible data. Despite its distance, Voyager 2 remained a functioning spacecraft. It continued to communicate, albeit slowly, using a transmitter weaker than a household light bulb, to send signals across billions of kilometers. Earth, listening with enormous antennas, responded with equal patience. This dialogue, stretched across vast distances and long delays, represented one of humanity's most enduring technical achievements: sustained communication across interstellar scales. As years passed, Voyager 2 moved farther into interstellar space, increasing its distance from the Sun by millions of kilometers each day. Its speed, built through gravity assists at Jupiter, Saturn, Uranus, and Neptune, carried it steadily outward. There was no propulsion, no guidance toward a specific star. The spacecraft followed a path determined long ago, shaped by planetary motion and preserved by inertia. This phase of the mission transformed Voyager 2 from a planetary explorer into a cosmic probe. Its measurements were no longer about worlds, but about space itself. Temperature, particle density, magnetic orientation, and radiation levels became the language of exploration. Through these quiet signals, Voyager 2 continued to expand understanding of the environment that fills the galaxy. Leaving the solar system was not an end, but a change in scale. The spacecraft moved from a neighborhood defined by familiar objects to one defined by distance and time. The planets were behind it, but their influence remained written into its speed and direction. Voyager 2 carried the history of the solar system within its motion, even as it left that system behind. The journey outward continued without urgency, guided by physics rather than intention. Voyager 2 did not know it had crossed into interstellar space. It simply followed the path it had been given, recording what it encountered along the way. In doing so, it extended human presence beyond the reach of the sun, carrying quiet measurements into the vastness between the stars. Voyager 2's journey did not end when it crossed the heliopause. In many ways, that moment marked the beginning of a quieter, longer chapter, defined not by encounters, but by endurance. Today, Voyager 2 continues to move through interstellar space, carrying instruments, memories, and momentum imparted decades ago. Its distance from Earth is best understood not in kilometers, but in the language of light, because radio signals now take many hours to bridge the gap between the spacecraft and the planet that built it. At present, Voyager 2 is more than 130 astronomical units from the Sun, a distance so large that sunlight there is more than 10,000 times weaker than at Earth. Radio signals traveling at the speed of light take over 17 hours to reach the spacecraft, and another 17 hours to return. This means that any exchange between Earth and Voyager 2 unfolds over more than a full day. Commands sent now were conceived yesterday, and confirmations received tomorrow describe events that are already history. Despite this distance, Voyager 2 remains an active scientific platform. A small set of instruments continues to operate, measuring plasma density, magnetic fields, and energetic particles in the interstellar medium. These instruments are not observing objects, but environments. They record how charged particles move through space, how magnetic fields align on galactic scales, and how cosmic radiation varies over time. This data is slow to arrive, but invaluable, because it represents the only direct sampling of interstellar space ever performed by a human-made object. power is the defining constraint of Voyager 2's present and future. Its electricity comes from radioisotope generators that convert heat from radioactive decay into electrical energy. This process is reliable, but not renewable. Each year, the available power decreases slightly as the radioactive material decays. To manage this decline, mission engineers have carefully shut down instruments and heaters over time, prioritizing those measurements most essential to the mission's final scientific goals. Voyager 2 is not failing. It is being simplified deliberately, step by step, to extend its life as long as physics allows. Eventually, within the coming decade, Voyager 2 will reach a point where it no longer has enough power to operate its transmitter. When that moment arrives, the spacecraft will fall silent. There will be no dramatic failure, no final signal announcing the end. Communication will simply cease. The last transmission will be received on Earth, decoded, archived, and preserved. Voyager 2 will continue onward, intact but unheard, carrying its trajectory forward without guidance or awareness. To understand Voyager 2's future path, it helps to think in terms of time rather than destination. At its current speed, Voyager 2 travels roughly 17 kilometers per second relative to the Sun. This is fast by human standards, but slow on interstellar scales. At this pace, it will take approximately 17,000 years to travel 1 light year. Long before that milestone is reached, human civilization may change beyond recognition. Languages will evolve, cultures will rise and fall, and the context that gave birth to Voyager 2 may become a distant historical footnote. Over the next centuries, Voyager 2 will pass through regions of interstellar space shaped by the local galactic environment. It will encounter variations in particle density and magnetic field strength, influenced by ancient supernova and the slow rotation of the Milky Way. These changes will not be sudden. They will unfold gradually, detectable only through long-term trends. Even after the spacecraft falls silent, its instruments and structure will continue to bear witness to these environments, though no one will be listening. In tens of thousands of years, Voyager 2 will drift through the outskirts of nearby stellar neighborhoods, though it will not closely approach any star. Space is vast, and even a journey lasting millions of years is unlikely to bring the spacecraft near a planetary system. Voyager 2 is not aimed at a destination. It is aimed away from origin. Its trajectory is a line drawn outward from the solar system, shaped by gravity and preserved by inertia. The golden record aboard Voyager 2 will remain intact long after its electronics fall silent. Encased in protective materials, it carries sounds, images, and messages from Earth as it existed in the 20th century. The record is not a message sent with expectation of reply. It is a time capsule, an artifact of curiosity rather than communication. Whether it is ever encountered by another intelligence is unknown and irrelevant to its purpose. Its value lies in what it says about those who chose to include it. Voyager 2's motion will continue for millions of years. It will orbit the center of the Milky Way, along with countless stars, gas clouds, and remnants of ancient explosions. Its path will slowly curve under the influence of galactic gravity, becoming part of a larger cosmic pattern. The solar system that launched it will continue its own orbit, gradually separating from Voyager 2, not because one slows down, but because both are moving within a rotating galaxy. In the far future, Voyager 2 will become indistinguishable from natural debris drifting between the stars. Its structure may eventually erode under cosmic radiation and micrometeoroid impacts, but this will take immense spans of time. For ages beyond human memory, it will remain a silent marker of a moment when a young technological civilization chose to explore beyond its immediate surroundings. Voyager 2 does not carry meaning by itself. Its meaning comes from context. It represents patience over urgency, curiosity over utility, and endurance over spectacle. It is a machine built not to return, but to continue. Long after its creators are gone, Voyager 2 will still be moving, carrying the imprint of its origin through a universe that does not notice, but does not prevent such journeys. As it travels onward into darkness, Voyager 2 becomes less a spacecraft and more a trajectory, a line extending outward from the sun, unbroken and unhurried. It carries no awareness of time, distance, or purpose. Yet in its quiet motion, it preserves a record of a moment when humans looked outward and chose to send something of themselves into the unknown, not to conquer it, but simply to know that it exists.
you